In this next unit, what we're going to be doing is an introduction to vector calculus. Vector calculus has applications in many diverse fields, especially physics and engineering, in the description of electromagnetic fields, gravitational fields, and fluid flow. You'll see how that would be when we talk about what a vector field is. Vector calculus is also used by meteorologists in modeling weather patterns and currents and tornadoes. Economists and financial analysts make use of vector calculus as well in some of their pricing schemes. So we're going to start by reviewing the types of functions that we've learned, and we're going to learn another function. So first of all, if we have a function from the set of real numbers to the set of real numbers, for instance, like y equals f of x. So we have a single variable going in, a single variable going out. That's the kind of function that you've studied for years. Its graph would be some sort of curve in 2 dimensions. Then the type of function we've been studying for the last 2 chapters is when we go from R2 or R3 and we get out a single real number. So for instance, like z equals f of x and y. We put in something 2-dimensional and we get out a real number. And the graph of that we found to be some sort of surface. These are both called scalar functions because what comes out is a scalar. So I just get a real number out. I don't get something multi-dimensional out. Just as a reminder, if you wanted to look back, this is chapter 14 and 15. Then in chapter 13, we did the kind of function that goes from the set of real numbers into R2 or into R3. Those we called vector valued functions, or just vector function. But the point is that we put in a real number and we got out a vector, either 2-dimensional or 3-dimensional. And the graph that with that would be either 2-dimensional or 3-dimensional curve in space. So the new kind of function that we're going to consider is the combination of this we haven't done yet, and that is we're going to go from multidimensional to multidimensional. Either we're going to look at R2 to R2 or R3 to R3. There are functions that go from R3 to R2 or R5 to R6. There's all those possibilities. These are just the only ones we're going to look at. And this type of function is called a vector field. That sounds like a strange name for a function, but you'll see why in a moment that it has that name. Okay, so here's this new kind of function. We're looking at the one right here that goes from 2 dimensions to 2 dimensions. This goes from R2 to R2. And this one would go from R3 to R3. So here's how it works. You put in something 2-dimensional. You can think of it as an ordered pair, or you can think of it as a vector. And you get out a vector. You get a function of x and y times I, and a function of x and y times j, which we could either write like that or we could write in vector form. So for example, suppose I have this vector function, which we call a vector field, which says take every point x, y, and you're going to get a vector out. And so just to kind of get a feel for how this works, when we evaluate functions, here we're putting in an x, y, and we're going to get out a vector f of x, y which is minus yx. So for instance, if I put in 2, 1, x is 2, so that goes here. Y is 1, so that goes here, negative 1. If I put in something like 1, 0, the y is 0, so I'm going to have minus 0, which is 0, and the x is 1, so 0, 1. If I put in 2, 0, y is 0 again, 0, 2. If I put in, say, 0, 3, then we'd get negative 3, 0. I'm getting kind of the feel for the pattern. What are we doing each time we're taking these two and switching their locations and putting a minus with that component? Kind of makes it easier if you see it that way. So for instance, if I put in negative 1, negative 2, I switch them and I take the opposite of y. So that's how it works as a function. You put something in, you get a unique thing out. We're putting in an ordered pair, we're getting out a unique two-dimensional vector. What would it look like if we tried to represent this visually, if we tried to graph it? So when I put in the point 2, 1, I get out the vector, negative 1, 2. If I drew a vector emanating from this point, that way, so left 1, up 2. So from the point 2, 1, I'm going to go left 1, up 2. I'm going to get a vector that looks like this. From the point 1, 0, so from here, I'm going to get the vector 0, 1, which just goes 1 unit up. From the point 2, 0, I get the vector 0, 2, so 2 units up. Maybe I'll make a different color so we can see the difference here. From 0, 3, from the point 0, 3, I get the vector that's negative 3, 0, so 3 to the left. From the point negative 1, negative 2, this is right 2, down 1. So negative 1, negative 2, the vector is right 2, down 1. Okay, so if we want to plot some of these functional values, we go to the ordered pair and we draw the corresponding vector. And so what that means is every point on here has a vector that goes with it. Sometimes if we want to try to get at that vector a little more quickly, we might analyze this a little bit. We might do things like, well, how about if I took anything on the x-axis? Whoops, if I took anything on the x-axis, what I mean is I'm putting in something on the x-axis, then the output vector is going to be 0x. We saw that here, 1, 0 became 0, 1, 2, 0 became 0, 2. So 0, 1, 0, 2. This one is going to be 0, 3. This one's going to be 0, 4. So you can see, you're starting to see a little bit of a pattern. They're getting longer as I go out. And actually, if x is negative, this still works. Negative 1, 0 would give me 0, negative 1. So 0, negative 1. Negative 2, 0 would be 0, negative 2. 0, negative 3. 0, negative 4. So you can get some graphs some vectors a little faster if you start sort of trying to generalize. Right? Another thing that you might do, another analysis that I sometimes see is something like this. And you'll see this more as we go on. But if I looked at anything in this quadrant here, the x component, the inputs, would have a positive x and a negative y. In that fourth quadrant, all these points here have a positive x, negative y. And so if we were to do that over here and put in a positive x and a negative y, then the vector that would come out, remember the x becomes the y. This component, whatever it is, becomes the x component, and we change its sign. So what that means is for every single vector over here, the outcome is going to be positive, positive, so up and to the right. So I'm not drawing them in yet. I'm just saying they're all going up and to the right. So the point being, if you want to make a vector field, sometimes you'll just plot some points like this, but sometimes you'll try to analyze and do something a little more general. One other thing that you might do here is if you notice that the magnitude of my vector output equals y squared plus x squared square root. And so that's telling me something about the vector 2. X squared plus y squared, think of a circle there. All the vectors on that circle have the same magnitude. As I go out, these will have a bigger magnitude. As I go out, these will have a bigger magnitude. So as x squared plus y squared gets bigger, think of a circle with radius getting bigger, those vectors get bigger. All right, so if I were going to fill in some more of those, what I'd ultimately get is a picture that looks like this. That is the vector field that I was drawing if I drew in more points. Now, this is defined at every real number, so every single point there is, even the ones that are white there would be a vector there too, but then, it would look solid. So this just gives me an idea of some of the vectors in our function, and this gives you an idea why it's called a vector field. So this is a vector field that describes the velocity vector of a rotating body. Notice as you get further out, those vectors are getting longer. That means that the velocity is getting higher out there, speed is getting higher. And so this would model some sort of rotating body. Here's a three-dimensional vector field function. And you can imagine that that might be used to model some sort of flow of wind or water or electricity. Here's some real-life vector fields. These are two-dimensional vector fields that are modeling wind patterns. This is actually San Francisco Bay. These are wind patterns or current patterns or air over airfoil. So this type of function has a lot of applications. This is how we model. I often talk about wind or water flowing just because we can really relate to that, but it models a lot of other things, gravitation. Okay? All right, so we actually have done a vector field. It's the first time we've called it a vector field. But remember when we took gradients? Here's this function here. If I take the gradient of this function, what it does is it creates a vector. Right? It takes the partial of this with respect to x, so 2xy, and then the partial of this with respect to y, which is x squared minus 3y squared. This function that we have here, this gradient function, this is a vector field because we're putting in something multidimensional and we're getting out something multidimensional. the gradient at any point in my domain was a vector, and that vector pointed me in the direction of maximum increase of my function. But that was a vector field. Okay? Vector fields that are formed in that way by taking the gradient of some scalar function, they have a special name. They're called conservative. A vector field is conservative if it is the gradient of some function. So if I take the gradient of some function to get that vector field, then that vector field is called conservative. The function that it came from is called the potential function. It's almost like here's a function, differentiate it. This is the antiderivative. Here's a function, take the gradient. This is conservative. This is the potential function that it came from. Okay, so in this example, this vector field would be conservative because I just took a gradient, and the potential function is f of x and y. Not all vector fields are conservative. And it's hard to know. If I gave you this vector field and I said, is this conservative, and I hadn't shown you this part of the problem, so if I was saying, did that come from taking the gradient of a function, I don't know. I didn't see anybody take a gradient. We're going to talk about that. How would we know if it's conservative if we didn't just take the gradient? But we'll talk about that more in section 16.3. Okay, so that's basically the section. We're just doing a quick introduction to vector fields. I did want to point out just some strategy. Sometimes people have questions on the homework problems where you have to do matching. You have to match a vector field to its graph. And so just to share with you there's lots of ways you could do this. You could put in certain points and see if it's pointing the way you think. But one of the things I do here, for instance, is I think, okay, let's consider the quadrant 1. In quadrant 1, I'm plugging in a positive and a positive. Every point here, the x is positive and the y is positive. All right? For number 11, that vector is going to be x, which is positive, and y minus y. So minus a positive number is negative. You with me? I'm just saying if x and y are both positive numbers, if x themselves and y are positive, this vector is a positive negative. That means that in quadrant 1, the graph for that vector field would be pointing to the right and down the whole time. In quadrant 1, everywhere in quadrant 1, to the right and down. Okay, to the right and down. Okay, it can't be that one. To the right and down. Oh, maybe it could be that one, but no, these are pointing up. Nope. To the right and down. No, those are going up. To the right and down. Yep, that's the only one. So process of elimination, just one little thing that I looked at, and I can tell that this one goes with number 11. As I said, this is not the only way to do it. Let me look at number 13. That's y and y plus 2. When we're in quadrant 1, y is positive. So positive, positive. Our outcome vector would be something positive, positive, which means positive x direction, which means right. Positive y direction means up. So in the first quadrant, we have to have all our vectors pointing upwards and to the right. Upwards and to the right. Do you see which one that's going to be? There's only one of them that matches that. That's this one. Upwards and to the right. This is going downwards, no good. This is going left, no good. So this would have to go with number 13. So that's some of the strategy that I use on those.